Good morning, everyone. My name is Miriam Jackson. I'm a third-year PhD student in chemistry, and my project is on conversion of sulfur-rich waste products into industrial important commodities. The research is sponsored by Tata Steel Steelworks, based in Port Talbot. So I'll talk shortly on history of steelworks in Wales and associated pollution problems, then extraction of sulfur from byproducts of coke making, and also I'll talk on synthesis of my catalysis and analytical techniques that we use as chemists, and at the end I'll talk a little bit on chemistry that I currently work on. Steelworks in Wales have a long history reaching to mid-19th century. The steelworks in Port Talbot, together with the docks and the railway, have been built on the Margam estate since 1901 and have been further developed ever since. The picture on the left then shows how the steelworks looked like in the 1950s. Today it is one of the only two remaining integrated steelworks in the UK. As for any other industry, the pollution is a major concern. One of the first steps in the steel production is coke making. Coke is made when coal is heated to 1200 degrees Celsius. However, the byproduct of this process is highly toxic coke oven gas. Coke oven gas consists mainly of hydrogen, methane, but also small amounts of ammonia and sulfur. In the past, the coke oven gas was released into the atmosphere, but now we know that many of the gases, like carbon dioxide, cause greenhouse effect. In addition, the sulfur, when mixed with air, creates sulfur oxides, which cause acid rains that are damaging to nature. Modern coke ovens are therefore equipped with fume hoods, which extract the coke oven gas. Some of it is then utilized on site. For example, hydrogen and methane are used as a source of fuel. But the industry still has problems with minor components of raw coke oven gas. In my project, I focus on sulfur in form of hydrogen sulfide. So this scheme shows where the hydrogen sulfide comes from. As mentioned before, the modern coke ovens have extraction hoods removing the raw coke oven gas. At first, it is cooled down and the tar is removed before it is passed through a washer. The water is injected into the washer, and as the gas is rising through the washer, it gets clean. The lean coke oven gas is then removed for further processing. The sediment at the bottom of the washer is also removed, and it contains hydrogen sulfide as well as other impurities like ammonia and naphthalene. So in my research, we wanted to take advantage of the presence of ammonia within this solution. So the idea was to pass air through the solution of hydrogen sulfide and ammonia in the presence of a catalyst to form ammonium sulfate. Ammonium sulfate is very important industrially because it's mainly used as a fertilizer, particularly in developing countries. As chemists, we can follow the reaction by infrared spectroscopy. This technique is looking at vibrations of bonds, in this case nitrogen-hydrogen and sulfur-oxygen bonds. Each such bond will have a specific peak, and each molecule will have a specific pattern, so they can be identified. For the catalytic transformations, we also need a catalyst. In my case, it is a metal complex. The complex is formed of a metal center, like cobalt, for example, or copper, and a ligand, which is a small molecule. In my case, it's a 2-bridged benzimidazoles. Again, as chemists, we can identify whether we form these complex molecules in various ways. One of the more specialized techniques is X-ray diffraction spectroscopy, which determines crystallographic structure of a molecule. But the most common technique for us is a nuclear magnetic resonance. It essentially works on the same principle as a magnetic resonance that is used in a hospital on a human body. It is extremely useful technique for us because it shows us not only the number of hydrogens but also the environment in which they are present. So, for example, on the left-hand side of this spectra, we can see these hydrogens are very acidic, and there will be the hydrogens that are close to the metal center. We can see there are two of them, on each side there's one. On the other hand, on the right-hand side of the spectra, there are CH3 hydrogens, and because we got two sets, there are 6 hydrogens, which are shown for these two terminal groups. In the middle of the spectra, we can see CH2's hydrogens, which will be these bridging ones. Once we have prepared these catalysts, rather than using them straight away on a complex system like the solution coming from the coke oven gas, we use model catalysis to determine the performance of such catalysts. I have used aryl halides and ammonium thiocyanate as my model compounds. The catalysts I've used are my copper complexes, and these reactions have been performed in water in the presence of a base. The preliminary results shows conversions of over 50%, which is expected at this stage. At the moment, I work on boron-containing ligands that can then be bonded to a metal center, for example copper or zinc, using a multistep synthesis. These syntheses are much more challenging as the materials are air sensitive, and so the special techniques need to be used to prepare these. However, the presence of the boron makes it easier to monitor the progress of the reaction. Boron is an active element in the nuclear magnetic resonance, so that we can see how the starting material is changing into a product over a given time. In conclusion, I have prepared and identified my catalysts that have then been used in a catalytic transformation of hydrogen sulfide and ammonia into ammonium sulfate. I am still in the process of purification so that the ammonium sulfate can find its use as a fertilizer, alternatively in water treatment or as a flame retardant. At the end, I would like to thank Gareth Owen Group for all the support and the hours of fun we have, and thank you all for listening and any questions.